Motivated from the least squares video, we are now going to look at orthogonalization. Orthogonalization. So the idea was, to recap, if I have my AX span here and if I have my B here, I want to be able to project B onto the space of AX. And one way to do it was to solve this normal equations. A transpose AX is equals to A transpose B. But we will never do this. Why? Because A transpose A has a condition number which is square of the condition number of A. And we do not like that. Instead, what we want to do is find a matrix Q and a matrix R, so that I can write A is equals to QR, where Q is orthogonal. It's an orthonormal matrix which has the same span as this, and R is just an upper triangular matrix which tells me how to combine these in order to get A. How to combine these orthonormal columns in order to get A. The main idea was, if I have a Q which has the same span as A and Q is orthonormal, I can project easily. I can do a very quick projection by just writing Q transpose times B is my projection. That's it. That's why I want to make a Q transpose matrix. Okay, so let's do that. First of all, let me discuss a few things about this. I mean, why is it even a good idea to do it? Is it a good idea to do it because if I had an A and if I applied, let's say, orthogonalization step by step, first step orthogonalization, second step orthogonalization, all of these matrices are orthonormal matrices. The condition number of this is the norm of Q times the norm of Q inverse, which is equals to the norm of Q times the norm of Q transpose, because the transpose is just the inverse. And both of these numbers are equal to 1. That means that orthogonalization is always a stable process. It has a condition number of 1. This matrix has a condition number of 1, which means it's a well-conditioned problem. So it's not going to cause any instability, any erratic behavior in our algorithm. So again, let's talk about how to do it. For example, this was my A matrix. A1, A2, A3, A4, A5. And this was I propose is a Q matrix. Q1, Q2, Q4, Q5. And here is I propose an R upper triangular R matrix. What this means is that A1, the first column A1 is Q1 times R11. The next column A2 is Q1 times A2 is Q1 times R12 and Q2 times R22. Q1 times R12 plus Q2 times R22, and so on. What is this? What is this procedure, so to speak? Well, this is constructing our Q matrix step by step. For example, my first column of this Q matrix is just A1 divided by R11, and I choose R11 as the norm of A1, such that my norm of Q1 is 1. It's a unit vector column. So what I do is, I first have my column, I take a norm of this column, divide it by that norm, and put that number in the first column of my Q matrix. Second, what do I do second? To find Q2, the second vector, what I do is A2 minus Q1 R12 divided by R22. What this is subtracting this. What I'm doing is I'm taking the column A2 and I subtract the part of A1 which is not orthogonal to A1. Essentially what I'm doing is taking A2, for example, if this was my A1 vector column, this was my A2 vector column. Once I decide that this is the direction of my Q1, I'm going to subtract this part of direction from A2. So now my Q2 will become this one. Basically what I'm doing is I'm removing the perpendicular bits of every column sequentially. Next, in A3, what I will do in A3 is subtract the perpendicular part of A1, subtract the perpendicular part of A2, and therefore what I have A3 right now is the orthonormal to both of these columns. What I have in terms of Q3. So for example, let me restate it again. First of all, let me be something very clear. I always think of matrices in terms of columns, which I think everybody does. It's like column, 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 and all of these columns are vectors, and matrices is just those vectors in a space. So what I take is I take the first vector and I say that the first vector is the direction of my first perpendicular column, first perpendicular vector Q1. I divide the norm of A1 from A1, I divide A1 by the norm of A1 and I have a unit vector in that direction. The next vector will be Q2, but then it's not necessary that A2 will be perpendicular to the Q1. So what I'm going to do is subtract the projection of A2 on Q1 from A2 and normalize A2 in order to have a perpendicular one in this direction. This is what I'm doing. This is Q2. Q2 is A2 minus Q1 R12 divided by R22, where R22 is just the norm of this. A2 minus Q1 R12. And how will I find R12? Well, R12 will be just Q1 transpose A2. Right? Let me look at this. Let me look at what I have written here. Yep, I've written it correct. Yep. So for let's say the jth column Vj, this is what I have written in my notes. Vj is Aj minus Q1 times Q1 transpose Aj times Q1 minus Q2 transpose Aj Q2 minus up to j minus 1 columns. All of the j minus 1 perpendicularly constructed columns. Next, Qj is just Vj minus norm of Vj. Right? So this is how my first naive algorithm works. This is known as the Schmidt orthogonalization, and given a matrix A, I construct Q in such a manner. First column first, second column second, third column third, and by constructing third column, when constructing the third column, I subtract elements from I subtract perpendicular items I subtract the parallel items of 1 and 2. When constructing a column 4, I subtract the parallel item of 1, the parallel item of 2, the parallel item of 3, and therefore I have whatever is left over is perpendicular to these things. So the invariant is on the jth column. Whenever I am filling the jth column of Q, it's perpendicular to all of the columns before it. And therefore, any next column is perpendicular to all of the columns before it. So the nth column is perpendicular to all of the columns before it, and therefore it's a unitary matrix. It's an orthonormal matrix. It's orthogonal and orthonormal by normalizing it. So yeah, I made it Q such that it's a unitary matrix. Why is this algorithm bad though? This algorithm is bad because at the jth step, I am subtracting aj from j minus 1 elements, and these elements could be the same size. So there can be cancellation. There can be catastrophic cancellation when doing Gram-Schmidt. So we have to modify this algorithm a little bit. We do a modified Gram-Schmidt orthogonalization in such a manner. At first, this is the idea. Like this is my A matrix. And I say that this is the same structure of my Q matrix. Now what I do is, I take the first column A1 and I subtract the parallel direction of A1 from each of these columns. So this becomes A2 minus some alpha times A1. This becomes A3 minus some alpha times A1. And I subtract the parallel bit from column 2 to n. From columns 2 to n. So now what I have achieved is, all of these columns, all of the columns from 2 to n are perpendicular to 1. That's all, the first step. In the second step, what I'm going to do is, take the second column A2 and subtract its parallel bits from the column 3 to n. So in the second step, what I have accomplished is, all the columns 3 to n are perpendicular to column 2. And in the first step, I had already accomplished that all the columns 2 to n are perpendicular to column 1. So I build this matrix in a separate manner now. I am not going to calculate every column right in one instant. Instead, I am going to do it iteratively. So my nth column, let's say I have the jth column. My jth column is subtracted by a number in the first step. My jth column is subtracted by a number in the second step. My jth column is subtracted by a number in the third step. It goes up till j minus 1 steps. So it's like my jth column was first in the direction of aj, but then in the first step it's refined a bit to point away from a1. Then it's refined a bit to point away from a2, not away, perpendicular from a2. In the next iteration, it's refined a bit to point away from a3. And by the j minus 1 iterations, it would have been refined to point away from a1, a2, a3, a4, a5 up to aj minus 1. Therefore, it's perpendicular to all of those previous columns. So it's like an iterative refinement of every column. This is known as modified Gram-Schmidt. Now this is better because I'm only subtracting once every step. Instead of subtracting a lot of numbers, which can add up to some cancellation, I subtract, let's say, a small number. I hope that in every iteration I'm subtracting a smaller bit of this. Instead of subtracting, for example, this is what I think is happening. If I have 1.00003, if I were to do direct orthogonalization, what if I subtract 1.00003 3, 2. This would lead to an error because 1.0000002 will not be stored in my computer. It does not have, let's say it does not have so much precision, so it might not be stored. But then doing it step by step, I hope is reducing some errors. It's a little bit better, that's all. It's still not the greatest algorithm. The greatest one is what we come to now. I just wanted to mention Gram-Schmidt and ortho or modified Gram-Schmidt because it exists. What we will talk about now is going to be household level, or another way of orthogonalization, which is not iterative refinement, things like that. So this is the idea. If I have a column in the matrix A1, let's say, or AN, which points this way, but I know I have a standard basis. Let's say this is the x-axis, this is the y-axis. So what I can do is, I can rotate this arrow to point in the direction of x-axis, right? I can rotate this. Or what I can do is, if I have my A, I can reflect this vector along another axis to point towards the x-axis. And if I do it for every column in my matrix, I will have them reflect and point towards a predetermined perpendicular direction. Then I reflect this to point towards the predetermined perpendicular direction. I reflect this to point towards a predetermined perpendicular direction. Slowly and surely, I would have reflected all of those A columns to point towards predetermined perpendicular orthogonal directions. That's what householder is trying to do. That's what householder reflector is trying to do. So for example, let me just write the main meat of the method. For example, if I have a vector A and I know this is a vector, this is the direction E1. E1 is a predetermined perpendicular direction. What I want to reflect to is I want to write a function which goes from A to alpha times E1, where alpha is the norm of A. Right? It's the same length pointing in the E1 direction. So basically what I want to do is let me make that projection here. So there is this plane on which I want to reflect, and this plane is perpendicular to this vector V, where vector V is A minus alpha E1. Right? This is the perpendicular vector V. This is the vector V, which is the perpendicular vector V. Right? So now to reflect this, to do this reflection, what I will do is I take my vector A and I take its projection on V, that becomes V transpose A divided by V transpose V, right? That's the projection of A on vector V. I subtract this in the direction of V. So what this becomes is this point, the projection on the plane perpendicular, but because I want to reflect it, I'm going to multiply it by 2 in order to take that subtraction direction one more step ahead. So this is what my householder reflection is. Identity minus, for any vector A, if I want to reflect it on a plane perpendicular to a vector V, I write my householder reflector matrix as I minus V transpose divided by V transpose V, but do not forget the twice. This is a householder reflector matrix. It will take any vector A and it will reflect to a plane perpendicular to V. This is the main idea of the householder reflector. Now how will I apply it to my A matrix? So what I want to do is, let's say let's say my algorithm runs successfully up till X iterations. So what happens is, I have converted this matrix which was completely filled with numbers, I converted it into, let's say, after J iterations, by doing householder reflections again and again and again, by applying Q, this matrix, some sort of matrix Q again and again to this matrix, I have converted it to an almost upper triangular matrix. Let's say I did it for 2 columns. Now, this is full and this is full. What I want to do is, I want to remove all of these numbers. I want to convert column 3 to an upper triangular column. That means only has 3 elements. So what I will look at, I will only look at the column only look at the vector which falls below this third line. So what I want to do is just look at this column 3 of this matrix. It is a dense column. I want to convert it into this x, and then another x, and then zeros. Because when I do this becomes a part of an upper triangle. So how would one go about doing that? How would one apply the householder reflector only to the bottom part of this? Well, I construct my matrix in such a manner. I'm going to make some specific numbers now. This is what has happened after 2 iterations, right? These 2 columns are correctly in upper triangular order. I'm going to write this as A1, A2, A3, A4, A5, and here is just junk. I mean, just the rest of the matrix. What I want to convert this column into is some bit x, this is x, this is correct. And here I want to do it x, and then 0, 0, 0, 0, 0. Yeah, 5 elements. And the rest of the matrix changed by the householder transformation. So I construct a matrix in such a manner. Identity and the householder matrix here. So when I apply such a matrix to this, what happens? I multiply identity with this part, this remains unchanged. I multiply this 0. I multiply identity with this part, it remains unchanged. I multiply 0 with 0 parts, this remains unchanged. I multiply 0 with this part, it turns to 0. And then I multiply the householder transform to this part, it turns to something. Yes. So this is what is going to happen. When I multiply my designed matrix to my iteration bit matrix here, I'm going to multiply identity with this part of the matrix. This gets copied directly. I'm going to multiply 0 with the 0 part, which does not affect at all. I'm going to multiply 0 with this upper triangular part, which does not affect it, and q to the 0 part, so this gets copied to 0. The next bit is I'm going to apply identity to this part, the upper part. It's going to get copied as it is. 0 to the lower part does not change anything. 0 to the upper part does not change anything, and q to this upper part gets reflected. So when I multiply q to this column 3 onwards matrix, I reflect the third column such that this becomes 1, 2, 3, and then 0, 0, 0. So I will construct my householder transform. I will construct this matrix in such a manner that I convert this column. 1, 2, 3, 4, 5 to 1, 2, 3, and then 0, 0. So to do that, all I need to do is just look at this bit of the column and reflect this to, so basically any 3-dimensional vector I want to reflect it to 1, 0, 0. This is how my householder matrix will be constructed, and you can fill in the rest. I mean, it's just reflecting again and again. So when I do the reflection on the first column, this is my pre-filled matrix A, right? All of these numbers are filled. Let me write it as a 4, 3 matrix. Let me take that as an example. When I do my first householder reflection, I pre-multiply it by Q. This is what becomes. When I do another householder reflection, this is what it becomes. X, 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 and then this one, 1, 2, 3, 4. 0, 0, 0, 0, 0. And when I do the third householder reflection, this is what it becomes. X, 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 this upper triangular matrix. 0, 0, 0. So now what I have found is, by multiplying those Q's again and again and again on the left hand side, I have turned it into an upper right triangular matrix. So just recapping a bit, letting go of the confusion, at the kth iteration, I turn the column, this big column, into 1, 2, 3, 4, 5 up to k, I mean k numbers and then 0, so that the kth column has only the top k elements in there. So this matrix turns out to be an upper triangular matrix, and I keep multiplying the reflectors on the left hand side, and it turns out to be this. So for the first column, I multiplied with Q1, where Q1 will be no identity, just the entire householder reflector. In the second iteration, I multiplied with Q2, where Q2 will be identity of length, identity of dimension 1, and the remaining householder. In the second iteration, I multiplied with Q3, which will be an identity of dimension 2, and the remaining householder, things like that. And all of these matrices multiplied are orthonormal matrices. So in the end, when I am multiplying this order, I will multiply it in the pre-order. What I have done is taken A, multiplied Q1, then Q2, then Q3, then Q4, and I have turned it into a matrix R. So how do I take it back? How do I take it back to that side? What I have to do is pre-multiply Q4 inverse, let's say. So that becomes pre-multiplying by Q4 inverse. Then I multiply by Q3 inverse. Then I multiply by Q2 inverse, which is nothing but the transpose. So I have to multiply by Q1 transpose, Q2 transpose, Q3 transpose, Q4 transpose, which is nothing but the transpose of this side. So all I have to do is keep multiplying these, keep this as Q transpose, A is equals to R, and then I have found my A is equals to QR. That's my householder reflection. That's my householder reflection algorithm. The confusion aside, the main point is all I do is find vectors A and reflect them on P predetermined perpendicular directions. And how I reflect them? I reflect them by using V. V is such that it's A minus the predetermined direction, the norm of A minus the A minus the norm of A predetermined direction. Just this. Now there is one thing that is interesting actually about this algorithm. When I do reflections, I have my vector A and I want to reflect it to E1, but I could have also reflected it to minus E1, you know. Instead of reflecting it to here, I reflected it to here. Why should I choose this over that, or what's the difference between choosing this over that? The idea is choose E1, choose the perpendicular direction which is farthest away from A, so that when I'm subtracting this bit, when I'm subtracting this direction from A and then subtracting it again, I'm not subtracting small numbers. If my A was, let's say, very close to E, by subtracting a small number, it's possible that I lose a lot of information in my system, because a small number like that cannot be stored by my system. Instead, I subtract it towards, I reflect it towards the one which is farther away, and that way I keep some stability in my algorithm. That's just the design, just the design part of this. That's householder reflection. Anything else that I want to say about householder reflection? Yes. Now we found out Q. Yeah, big deal. What about it now? We wanted to solve the system. We wanted to solve this. B minus AX minimum. We wanted to solve this. Well, multiplying it with Q transpose doesn't really change its norm, right? Q transpose is a unitary matrix. All it does is just rotates the space in a certain fashion, or reflects it in a certain fashion. Doesn't change the volume, or doesn't change the norm of this thing. So all I'm going to do is multiply it with Q transpose. This becomes Q transpose B minus Q transpose AX. No. Now to pay attention here, Q transpose B is going to be something like something. However, Q transpose A is just the matrix R, right? It's just the matrix R. But R matrix will be an upper triangular matrix with some columns as 0, right? With some columns as 0 in the bottom. If I have m greater than n, right? The number of this is what I mean. Let me do it again. A is QR, right? I write A as Q1, Q2. I just split it into 2 because my R matrix looks like this. There is an upper triangular part and then there is a 0 part. So my A essentially is Q1 times just the R. The Q to 0 is just lost in translation. It's just lost. So what is my so my Rx Q transpose AX minus Q transpose B. Right? This is correct. This is correct. Now I write Q transpose B as B1, B2. Right? I'm just multiplying Q transpose B with that, and I'm going to subtract. Q transpose AX, where Q transpose A is just R and R, because of this nature of R, all this becomes Rx is just going to be R1x and 0. Right? This is what it is. Rx is R1x 0. So Q transpose B minus Rx becomes B1 minus R1x and B2 stacked on top of each other in one vector. So what is the x which minimizes the norm of this thing? Well, the x that minimizes the norm of this thing is B1 equals to R1x. So x is equals to R1 inverse B. X is R1 inverse times B, and the bias which will, oh sorry, not the bias, the residual which will never be changed is B2. I mean, B2 is the minimum of that value which we are trying to minimize. So bring me back to this AX and B. This will be the X and this will be that B2. This is just the residual, that is B minus my final answer. This is the residual. This will give me an X which minimizes this. So this can also be interpreted in such a manner. The B1 minus R1x is the direction in the contribution to error in the subspace, in the space of the A. This is the first one, and B2 square is just the contribution to error in the perpendicular space. The perpendicular space, we can't do anything about it because that's just perpendicular. We can't reflect the perpendicular part onto this, but the one which has some component in the space of, in the range of A, we can reflect that, and that we can project that, and that is given by this. So anyway, the point is, after you do some householder reflections, all you have to do is look at the upper triangular part, do the inverse, and multiply it to B. That will be your answer. That's it. That's all. That's what I wanted to say about householder reflection. So R1 inverse B is the solution and B2 is the residual. That's it. That's about linear squares. So the condition number of a linear squares problem depends on the angle. How much is the angle of B to this subspace, this range space of A? If it's a very big angle, that means even the slightest change in B will have a lot of effect in my final solution. If it's a very close enough, if this angle is very close, that means a slight change in B will only result a slight change in A, in the solution X. And how would we do it? We could have solved the linear least squares problem by solving the normal equations. But don't do that. Don't ever do that. This is one of the sins of linear algebra, because A transpose A has square condition number of A. So we don't do that. Instead, what we do is find Q, which has the same space, the same column space as A, but has perpendicular orthonormal basis. So we can directly project B using that orthonormal basis, and we use QR decomposition to find that orthonormal basis, and one algorithm to find the QR decomposition is householder reflection. That's it.